but you don't have to. Yeah, but it's yeah, it's not all. It's not black and white. Um, so we're going to talk about translations. Yeah, my wife went to alternative high school and she never took math. So to get into college, she had to do like some special class to get into college. And she studied film. She has a fine arts degree, and now she's a computer programmer. So you never know how things are going to turn out. Yeah, yeah, yeah. You never know what happens. Um, my father-in-law was in Vietnam, and now he's an astrologer. With the zodiac? Yeah. It's kind of interesting. You never know what's going to happen. All right, so we decided a transformation is some kind of change. So just to make it a little more relevant to what we're doing in geometry, we're just going to say we're going to change a geometric figure. That's what we're talking about. Somehow. We're going to talk about 4 different transformations. 3 of them are called rigid transformations. So our 3 rigid transformations, and basically what we do is we talk about 1 transformation per day for the next 4 days. Our 3 rigid transformations are the first one that we're going to talk about today, a translation. So what are you going to guess a translation does to a figure? Yeah, it just moves it. It slides it. The second one is a rotation. And what do you think a rotation is going to do to a figure? Rotate it. Yeah. And the last rigid transformation is a reflection. Yeah, and what do you think that's going to do? Reflect. And I'm going to add one thing, over a line. So when something is like the mirror, so we're going to reflect over a line. And what's important about the rigid transformations is they stay the same. Yeah, our shapes stay the same. And I'm going to say the same size and shape. That's why we call them rigid transformations. So if we have a shape and after we do something to it, the new shape that we get is the same size and same shape, how are those 2 shapes related? What did we say about shapes that are the same size and same shape? They're congruent. So rigid transformations make congruent figures. We say that they preserve length, the other way that we say it is distance, so the distance between points, and angle measure. So rigid transformations preserve length and angle measure. So they don't, nothing about the shape changes other than where it is, its orientation somehow. And when we first started talking about congruent shapes, we said a little later we could make the idea of congruent more technical. With transformations, that's how we make a more technical definition of congruence. We say that two shapes are congruent if one is a rigid transformation of the other. So that's a more technical way, a more precise way we can define congruence. All right, so what I want to do is we're going to talk a little bit about rigid transformations first, and then we'll specifically talk about translations. So I'm going to draw some pictures, and we want to decide, is this a rigid transformation? So here's the first couple of shapes. So here's one, and here is the other. Is that no? What's the problem here? They're not the same shape. Well, they're triangles still, but they're not the same triangle. They're not congruent. Angles are different. The side lengths are different. Not congruent, so this is going to be no. How about this? Look at this. I want that. How about that? Yeah, if I drew everything perfectly, that could be a yes. Because what have we done to the shape? Yeah, we just slid it over here a little bit. Maybe it's possible that it reflected over something, but that looks like a rigid transformation. What we get after is the same as what we had before. How about this? Let's see if I can do this. I don't know if I can do this well enough. No. No. I'm going to have to use this. All right, how about that? Yeah? What could that one be? Yes, that could be a reflection. Is there anything else it could be? It could be a rotation, right? Around that point. So, but the triangles look the same. So that could be a reflection, it could be a rotation. So those could represent rigid transformations. Rigid transformations don't change the size or the shape of the thing, the figure. All right, so we want to talk. What we want to do with transformations is describe them with math. We don't just want to say, oh, we slid it. But we want to say, okay, we slid it this much in this direction. We don't want to just say, oh, we reflected it, but we reflected it over this line. We rotated it 20 degrees around this point. So we want to be able to what we call quantify. We want to put numbers to it. So that's what we want to do next. With transformations, our original figure is called the pre-image. And after the transformation, we have the image. So we take a shape, we call it the pre-image, we transform it, that gives us the image. And we use an arrow and what we call prime notation. So if we transform a triangle ABC is transformed to triangle A prime, B prime, C prime. And the way we would say this is triangle A prime, B prime, C prime is a transformation of triangle ABC. Or we could also say triangle ABC maps to triangle A prime, B prime, C prime. So that's how we would say that in words. And triangle ABC would be the pre-image, and A prime, B prime, C prime would be the image. And this also tells us that A corresponds to A prime, B corresponds to B prime, C corresponds to C prime, angle A corresponds to angle A, angle B corresponds to angle B, etc. So it tells us what parts match up, just like when we had congruent statements or similarity statements. So this little thing, we don't have a special name for it, tells us how the parts match up as well. All right. Well, now we're ready to talk about translation. What a translation is. A translation is a transformation, a rigid motion, that maps. The other way you read it or hear it described is or takes or moves. All of these words will be used to describe a translation. Map is the more general one. All points of a figure the same distance in the same direction. Same distance means we don't move one vertex of a triangle 3 feet and another vertex of the triangle 20 feet, because that would stretch the side. And we move all the points in the same direction. We don't move one vertex up and the other vertex sideways. We move all the vertices in the same direction, because then that would distort the shape. So that's our definition of a translation. All the points move in the same distance, the same direction. And we write translation, capital T for translation. And down here in brackets, we put some numbers, x, y, of triangle ABC, for example, for a triangle, equals triangle A prime, B prime, C prime. And this gives us our rule. The x tells us how far left or right we move, and the y tells us how far up or down. And we'll do an example here in just a second, but this is how we decide how much we move. We go left 3, down 4, right 2, up 5. So that's going to be our notation for a translation, the capital T, and this tells us how much we translate, how much we move. All right, so let's look at a couple of examples using a translation. Any questions before we go on? So part of what we're going to do in our project is you're going to come up with a shape, and you decide what the translation that you want to do to it. And then you'll transform it, and you do a translation, and then you'll, on a piece of graph paper, you draw that new translation. So, for example, we want to know the vertices of a translation, capital T means translation, of -3, 4 of triangle RST. And I'm going to draw, so we're going to have RST on a graph. So R is going to be at 1, 2. S is at 4, 1. And T is at 1, -3. So my triangle is here. I know my plots aren't beautiful and perfect, but we get the idea. Well, the rule tells us says the -3 tells us 3 left and up 4. So we move every point on the triangle, 3 left and up 4. So really all we have to do is move the vertices, sketch the new vertices, 3 left and up 4. So what this means is -3 from the x and +4 to the y. And that's how we're going to get our new points. So R prime is the point 1 -3, 2 + 4. So that point, 1 -3, -2, 2 + 4 is 6. S prime is going to be 4 -3 and 1 + 4. So that's going to be the point 1, 5. T prime is 1 -3, -3 + 4. 1 -3 is -2, and -3 + 4 is 1. So there are our new vertices. And if we plotted these, see if I can do this, -2, 6. So there's R prime at -2, 6. There's T prime at -2, 1. And S prime at 1, 5. -1, 5, sorry. And my new triangle translated would be there. And I know my drawing's not perfect, but we slid it over. That would be roughly what it would look like. So translations, we're just adding or subtracting numbers from the vertices. And we find our new vertices. All right, questions? We can also go the opposite direction. If we have our triangles or our shapes, we can figure out what the rule is. So let's do an example of that. So we want to know, what is the rule? For the translation. So here's my picture. All right, and I'm going to say this is n, and it is at -3, -1. And this is m, and it's at -2, -3. And this is L, and it's at -5, -4. And this is L prime at 1, -1. M prime at 4, 0. And this is N prime at 3, 2. So we're transforming the image LMN to L prime, N prime, N prime. And we want to know what the rule is. So we want to write our transformation rule. So all we have to do here is pick one vertex and decide what we're doing to the one vertex to get to the new vertex. So let's pick, I picked n. What do we do to go from -3 to +3? Add 6. So we're going to add 6 to x. What do we do to go from -1 to 2? Add 3, plus 3 to the y. So our transformation rule would be translation of 6, 3 to LMN equals, should be a triangle, L prime, N prime, N prime. Tells us we move right 6, up 3. And that's all we have to do. Yeah?
The brackets have to look like that.
The brackets are straight angly brackets. We'll use different kinds of brackets for different transformations. All right, I want to do one last example with a slightly different idea. So this one has to do with city blocks. So we're imagining that our house is on a nice grid city block, yeah? Yes. All right, so we leave our house. And we go 2 blocks east and 5 blocks north to the store. Then we go 4 blocks west and 1 block south to the friend's house. And we're saying our house is at 0, 0. So our house is where we start, 0, 0. We want to know how far from home. So we want to know how far east or west, how far north or south. So if I go 2 blocks east and then 4 blocks west, how far have I gone? What is it? 2 blocks west. So we go 2 blocks west. And if I go 5 blocks north and 1 block south, how far have I gone? 4 blocks north. So we could say, we could call this a translation of 2, 4. If this is east and west and this is north and south. But it would be enough to say we're 2 blocks west and 4 blocks north from home. All right, questions? Okay, our homework, page 550. Number 8 through 32 even.